A Memorandum of Understanding (MOU) between University Technology Mara and Brave Oil Field Service and Engineering (BOSE) was made on 1 March 2022. From the MOU, a study about water desalination plant at oil rig platform has been conducted as stated in Dagang News, where there are two students are conducting the studies through the engineered simulation with fulfillment of IR 4.0 standards with a method of 21st century AI issue solving through the method of computational fluid dynamics (CFD). Therefore, the technology readiness level and definition is at level 7 for this method, since it demonstrates the prototype through a picture for visualization. In support to Sustainable Development Goals (SDG) of SDG 3 and 6, this method will reduce the time consumption and incurred costs where this method is a rapid solving method with accurate and verified results or output. This study also had a technical reference from the MOU engaged company BOSE Sendirian Berhad with UiTM, where this will possibly be a good reference for the oil and gas industry. This study had registered with the Intellectual Property Corporation of Malaysia, known as MyIPO. Now, I want to present one of the study from the MOU, which is titled Computational Fluid Dynamics (CFD) Study on Mechanical Losses for Desalination Water Distribution System at Oil Rig Platform Facilities. The oil and gas industry, especially offshore, has faced a shortage of fresh water due to high usage of clean for certain operations such as drilling or production processes. Normally, offshore service vessels (OSV) that are responsible to deliver and transport the water supply from the shore to the platform had faced several problems due to a breakdown or waiting suitable weather condition. For this challenge, it can be solved by installing a desalination plant where reverse osmosis is the common purification technology that requires 1,200 psi of operation pressure. The seawater has to travel through a piping from sea level to the desalination plant with 110 feet of elevation, where the 90-degree elbow has the highest pressure drops compared to other fittings, as a piping system consists of branching T, valve, and a straight pipe. These pressure drops will reduce the operating pressure in the system. Thus, the pressure drops need to be minimized so that the desalination plant can operate efficient, where the seawater can penetrate the semi-permeable membrane more easily. There are two objectives for this study. For the first one is to investigate the mechanical losses in the aspect of pressure drops inside the 90-degree elbow. The second one is to obtain an optimum design of the 90-degree elbow for the piping of desalination water system. For the methodology of this study, the selected turbulence model is realizable K-epsilon model, where this model is suitable for a single phase and complex flow. There are two geometry of the 90-degree elbow, which is pipe curvature ratio equals to 1, known as PCR1, and pipe curvature ratio equals to 2, known as PCR2. Pipe curvature ratio is a ratio of curve radius over diameter, so if the pipe curvature ratio equals to 1, then the curve radius actually equal to the diameter of the pipe. Meanwhile, if pipe curvature ratio equals to 2, then the curve radius is double of the diameter of the pipe. From the figure on the right side, it is a checkup rig with the piping of desalination water system, where it shows the location of the piping system. This study focused on jackup rig applications, since jackup rig is the common rig that been used in Malaysian water. A piping system consists of vertical and horizontal positions of 90-degree elbow, where each of these positions will be implemented with two types of curvature ratio. This simulation will cover this position as a comparison and determine which position will produce higher pressure drops. There is no study that makes a comparison between vertical and horizontal positions with different curvature ratios, and Reynolds numbers were conducted especially for water desalination piping systems with seawater as the fluid medium. After designing the geometry to the computer-aided design (CAD) software, the model is transferred to the Computational Fluid Dynamics (CFD) software for generating the meshing for each of the models. The hexahedral cells are used for the simulation, since hexahedral cells are more accurate compared to tetrahedral cells, but bearable to polyhedral cells, since hexahedral cells have less computational time for generating the mesh compared to other cells. After generating the mesh for each of the models, the Grid Independent Study GIS need to be made is to identify the minimum number of mesh elements therefore providing less computational time with high accurate result. Based on the result on the right, the selected mesh element range is 960,876. For your information, this simulation is conducted on student version CFD software, where it has limitation for mesh elements that up to 1,048,576. After conducting the GIS, validation is a must and performed to ensure the credibility and reliability of simulation. As you can see here, the validation is conducted by comparison between present study with Dutta et al. From the graph on my right, it shows that the trend of the pressure difference between present study and Dutta et al. Is almost identical. It tells the study on the correct path. After conducting the validation, CFD setup is taken where the fluid that being used for the simulation is seawater at 300 K with density of 1019.7670 kg per meter cube and dynamic viscosity of 0.001199 pa per second. The boundary condition is inlet is set to velocity, outlet is set to atmospheric pressure, and wall is set to no slip condition. For the result of pressure contour for PCR1 and PCR2, it can be concluded that PCR1 has a denser color compared to PCR2 at Re equals to 10 times 10 to the power of 5. The denser color indicates the fluid is more resistant to change in direction or redirection of the fluid flow due to mild curve. The color of pressure contour starts from less to denser color. That tells the Reynolds number is influenced the pressure contour as well as the curvature ratio. This is the comparison of pressure differences between vertical and horizontal positions. The pressure difference for vertical position is slightly lower compared to horizontal position due to the direction of flow at vertical position is against the gravity. It can be summarized between vertical and horizontal positions that PCR1 has a higher pressure drops compared to PCR2. For the result of velocity vector, it can be concluded that the PCR1 has a denser color compared to PCR2 at Re equals to 10 times 10 to the power of 5. The denser color indicates the fluid head phase a severe change in direction of fluid flow that leads to a high velocity. The color of velocity vector starts from less to denser color that tells the Reynolds number is influenced the velocity vector as well as the curvature ratio. The graph on the left shows the PCR1 has the highest velocity compared to PCR2. This velocity is taken at the entrance of the downstream pipe. This high velocity indicates the fluid has a tendency to detach from the inner of the wall and creates a separation flow. For the result of wall shear vector, it can be concluded that the PCR1 has a denser color compared to PCR2 at Re equals to 10 times 10 to the power of 5. The denser color indicates the wall had a huge friction from the fluid with high velocity. The color of wall shear vector starts from less to denser color that tells the Reynolds number is influenced the wall shear vector as well as the curvature ratio. The graph on the left shows the PCR1 has the highest wall shear stress compared to PCR2. This wall shear stress is taken at the exit of the upstream pipe. This high wall shear stress indicates the fluid has the tendency to detach from the inner of the wall and creates a separation flow. For the discussion of the result, the separation flow happens at PCR1 at Re equals to 10 times 10 to the power of 5 when the wall shear stress or velocity at the specific area is nearly to zero. The fluid starts to detach from the wall and creates a recirculation zone where this zone contributes to the pressure drops. Since this zone has become the obstacle for the fluid to travel inside the pipe, it can be concluded that the separation flow happened due to a severe change of direction of the fluid that leads to high velocity and wall shear stress. The separation flow needs to meet the reattachment flow since the longer the distance between separation and reattachment flow, the higher the pressure drops. The design of the 90-degree elbow needs to be smoother as it has lower velocity and a wall shear stress factor as shown in the figure. This happens when a smoother elbow has a higher surface contact area that leads to moderate change of direction of the fluids and lowers the velocity. Thus, through analyzing this criteria, the distance of separation and reattachment flow can be minimized. In conclusion, the PCR2 is the recommended and selected geometry due to its ability to maintain smoother flow and low pressure drop that is contributing to higher overall efficiency in the system. Thus, this geometry can adapt the work environment up to Re equals to 10 times 10 to the power of 5. Thank you.